All right, it's everyone's favorite time. Word problem time. Hooray, I know you're celebrating. I did lie to you again in the last video. This one will be the last video of the series. So because I realized I could cover two concepts in one video, we can figure out how to do a word problem and in the same word problem do the derivative for a what's called quadratic, okay? So we got a situation here. The height of a baseball t seconds after it is thrown. So a baseball is thrown. Once upon a time, a baseball was thrown. And the height of that baseball changed with respect to time, right? If you throw a baseball, it usually goes up and then goes down, right? So the vertical height is going to change as after you throw it. Here's the equation, okay? It's a quadratic, a parabola that faces downward. Yes, projectile motion can be modeled with parabolas, and in fact, it almost always is. Where h, the height, is given in feet. Okay, so I plug in t amount of seconds, and this function will tell me h amount of feet, how high the ball is, right? Find the vertical speed of the ball 1 second after it is thrown. So this ball is thrown, and after 1 second, I want to know what's the vertical speed. Okay, not the speed of the ball, because the ball is probably traveling horizontally as well. I just want to know what's the vertical speed. Kind of like how when we were dealing with vectors, a object in motion has a vertical and a horizontal speed that you can represent with vectors. This ball is probably moving like this. I want to know just the vertical speed of it. Okay, and we can do that using calculus. Okay, so first let's get an idea of the situation. If you graph this, it looks something like this. You get a downward facing parabola. Okay, here's 0. Obviously the ball doesn't go under the ground. We're going to assume that this is 0 height. That's from the ground. It's thrown from the ground. It goes up and then it comes down. If you graph it, the highest point is a little bit over 6. I think it's at 6.25. So that's how high it goes at its maximum. And then it hits the ground like here's 1 and here's 2. So it hits the ground somewhere between 1 and 2 seconds. Okay. And we want to know what's the speed of the ball after 1 second, right? Here's the ball, 1 second after it's thrown. What's its vertical speed? How fast is it moving? It looks like at this point it's moving down, so it probably has a negative speed, a downward speed, okay? So it turns out that the speed of the ball at this point is the derivative of the function at this point. Okay, why are those things the same? Why is the speed the same as the derivative? Well, a speed, if you think about it, is a change in distance over a change in time, right? Miles per hour, feet per second, a change in distance, how far you've traveled over a certain amount of time in which you've traveled that, right? So, well, let's think about the derivative here. Remember, the derivative at any point is the slope of the tangent line, right? Well, the slope, remember, is the rise over the run. So if this is our tangent line, and that's the thing we want to find the slope of, well, the rise of the tangent line, let me refocus this here. Okay, what does the rise of this tangent line represent? Well, the y direction of my graph, this is h, and the x direction is t. I have h versus t. H is represented in feet. Okay, vertical feet. You can see it up here. H is given in feet. So this vertical rise of my tangent line is a change in feet, right? So that's measured in feet. And the run of my tangent line, well, that's a change in the x direction, okay? So what's my x-axis represented by? It represents time, right? So my height, my rise of my tangent slope is a measurement of feet. The run of my tangent slope is a measurement of time, which is given in seconds, right? Where is that? It tells us that, yeah, t seconds, says that at the start of the problem. So this is really measured in seconds. So I really have a measurement of feet per second. At that instant, the speed of my ball has a value in feet per second, and we can find that value by getting the slope of that tangent line. Okay, hope that makes sense. The same would be true any point on this parabola. Okay, if it was just a half a second after we threw the ball, it would have an upward velocity, right? And the change in height over the change in time, the rise over the run, would tell us its velocity at that point. Okay, so when you get a problem like this, which there's gonna be one kind of like this on the quiz, all it's asking for is the derivative. Find the derivative of this function at this x value, or in this case, it's a t value. Okay, so that's all we're doing here. Let's find the derivative. So it's the limit as, you know what? I shouldn't use as h approaches 0 because I already have h as my function variable. You know what? Let's change this to f. That way we're not confused. Good old f of x, except this time it's f of t. Okay, so this isn't h, this is f. It's the height of our ball. Okay, so the limit as h approaches 0, we'll use the h that comes from our derivative equation. Sorry about that, I didn't want to confuse you with two different h's. So the limit, we have the same function, f of x plus h minus f of x all over h as h approaches 0. This is the rise, right, over the run of our secant line. And our run, we want to shrink that to 0 to get the slope of the tangent line, which is this line right here, which tells us the speed of the ball at 1 second. Okay, so first we need to find f of x plus h, and we'll find f of x. We'll start with f of x. F of x, well, that's just f of 1 since we're looking at, okay, I realize now that I'm saying f of x when really I mean f of t, right? Because our x-axis is time. So really this should be a t, and this should be a t. Okay, I'm not going to re-record this video again. I've already done it once, and I'm just going to go with it. Okay, so you'll just have to bear with me here. These mistakes, those are supposed to be t's. So instead of f of x, we have f of t, which is f of t is 1 second. And I just pop that into my function. Negative 16 times 1 squared plus 20 times 1. And we just get negative 16 plus 20. That's positive 4. So f of t is 4, and I'll pop that in there. Let's also find f of t plus h. F of t plus h, well, that's going to be f of, well, t is 1, so 1 plus h. So we just plug 1 plus h in there for our function. Negative 16 times 1 plus h squared plus 20 times 1 plus h. We got some simplifying to do here. I am going to square the 1 plus h first. So I got negative 16 times 1 plus h squared. I don't distribute the exponent here. That rule, even though it's quarantine, even though the whole world is different, one thing doesn't change, right? This whole coronavirus has flipped your world upside down. Mathematics stays constant. You still cannot distribute that exponent in there. We've got to FOIL that, and I'm going to do that quickly here. 1 squared plus 2h plus h squared. Okay, if you don't, that's just the square of a sum. Square the first one, square the second one, and then add 2 of the product of the two. Okay, plus, and I'll distribute the 20 here. 20 plus 20h. Okay, we can distribute the minus 16. We get negative 16 times 1, that's just negative 16. Negative 16 times 2h, that's negative 32h. Minus 16h squared. Plus 20 plus 20h. We'll simplify that one more step. Oops, that's off your screen. Simplify that. Yeah, one more step before we plug back into our derivative equation. We can do, let's see, negative 16 plus 20, and that'll give us a 4, and I'll put that on the right. We got negative 16h squared here, and negative 32h plus 20h becomes negative 12h plus 4. Okay, so there is f of t plus h. So I'll take f of t plus h, and I'll take f of t, and we'll put those in here. Let's see, am I going to have enough space on this page? Probably not. Let's go to a new page here. So I have the limit as h approaches 0 of f of t plus h. What's that again? Negative 16 h squared minus 12h plus 4 minus f of t, which we figured out is 4, so minus 4 all over h. Okay, now we can just focus on finding this limit. Hey, that's nice. 4 minus 4 is 0. So I'm just going to get negative 16h squared minus 12h all over h. Limit as h approaches 0 of that. Let's see, can I put a 0 in there for h yet? No, because I still have an h as my denominator. What can we do? Some of you see it already. H is a factor of my entire numerator, and it's a factor of my entire denominator. So I'm going to show this step, negative 16h minus 12 all times h, factoring out the h, right? Dividing an h out of there, dividing an h out of there. We pull it out. What's left? We get negative 16h minus 12 all over h. Now we see that division we can do, right? H is a factor of the entire numerator. H is a factor of the entire denominator. H divided by h is 1. So we get limit as h approaches 0 of negative 16h minus 12. Okay, now can we substitute 0 in for h? Yes. Okay, h can approach 0, and when h hits 0, we just get 0 for that term, right? So really this just equals negative 12. Does that answer make sense with our problem? Does that seem like a correct velocity of a baseball 1 second after it's thrown? Where did I put my paper? There it is. Remember, 1 second after it's thrown, we have this velocity. Does it seem right that this line would have a slope of negative 12? Yeah, because that is obviously a negative slope. Okay, so there you go. That is how you can use the derivative to calculate something that's actually concrete and physical in real life, the speed of a baseball. This equation is actually a legitimate equation that would represent projectile motion. Something that has a speed of 20 feet per second sent in the vertical direction would have a negative acceleration of equal to the gravitational constant, which you guys learn in physics, which is about 32 feet per second squared. And this negative 16 is exactly half of that. And that you can derive this using calculus that you'll learn later. Okay, so this is a legitimate equation. This isn't just something I pulled out of thin air. So we actually did just calculate what would be the speed of a ball that is hit upward or thrown upward with a velocity of 20 feet per second, and then gravity starts to work on it. What would be the downward speed after exactly 1 second? We just figured out that would be negative 12 feet per second. So there you go, calculus used in a real world example. And that will do it for this series. Don't forget to do the practice problems that I put in the module, and don't forget to actually go through the Canvas lesson. There's 3 practice problems there if you feel like you need more practice. And once that's done, good luck on that quiz, guys. I will see you in the next series. Bye now.